Dank u, Dr. Mikitu. Before we move to the next subject, well, we have no time, so please. Part of my answer under the control of Dr. Mikitu is that some of the progress is not visible. For example, things like harmonizing, let's say, objectives for fast Newton reactor safety, let's say in Europe. Well, it is something that is not visible really on a view graph. Also, we should remind the fact that SNE was launched 10 years ago. Before that, it was politically not accepted that we would really cooperate in Europe for future nuclear energy systems. And then there was no cooperation on fast. There were bilateral or multinational cooperation, but not within. And I think that besides sodium-cooled fast reactors, that was really on the track. So the emergence of lead-cooled fast reactors or molten salt reactor is part of the, let's say, path that has been achieved in over the past decade. Even though, let's say, this is just the beginning of the story in terms of building competencies and building, let's say, research facilities to be debated. Thank you again, Constantine. And now from fast reactors, we move to the nuclear fuel cycle. And the next presentation will be delivered by my colleague, Stéphane BOURG. So from CEA, he's a project manager in charge of international cooperation at CEA Research Department of Mining and Fuel Recycling Process. Stéphane has worked on pyrometallurgical processing in the early 2000s and was since 2008 the coordinator of the European research projects about hydro and pyro separation process development for spent nuclear fuel reprocessing. So the projects accept success and GENIORS that he will cover. Beyond that, his research activities also cover life cycle assessments of energy systems and raw materials value chain analysis. Stéphane, please.
Thank you very much, Frank. Good afternoon, everyone. Since yesterday, we heard a lot about the interest of nuclear energy for climate change, for sustainability, and also we heard a lot about machines, reactors, their safety, their efficiency. But if I could make a comparison, I think that we discussed a lot cars without building any roads. And what I will show you now is how can we build roads, that is the fuel cycle that we need around these reactors through 3 projects. But before, I will present you an introduction to position the fuel cycle and how this fuel cycle can really bring the sustainability in the system. And then I will present you rapidly. You will see a lot of slides just to illustrate the main highlights of the different projects. So as an introduction, there are different ways to operate the fuel cycle. The first one, the most applied in the world, is the open fuel cycle. If I could illustrate this with the French situation, if we imagine that the French fuel cycle is an open fuel cycle, we would mine about 10,000 tons of natural uranium just to prepare 1,200 tons of spent fuel and just to burn 70 tons of uranium. So it means that the global efficiency of the use of the uranium resource is less than 1%. So today, if you explain me that nuclear energy is sustainable, I don't follow you. So how can we increase this sustainability? The first way is what we call the twice through cycle, so the twice through cycle or the French fuel cycle. By using this spent fuel once as a MOX. With this, in France, we can save about 20% of the natural uranium resource. And then, wow, we have a global efficiency of the uranium resource of 1%. Great, from 0.7 to 1. But we are far from a very efficient use of the uranium resource which is a limited resource on Earth, of course. And then the next step, we are discussing this for 2 days almost already, is the fast Newton reactors. They totally change the picture, of course. As you know, fast reactors can use efficiently the 2 isotopes of the uranium, 235 for the fission, 238 for the transmutation. And if we try to imagine what would be the efficiency, the global efficiency of all the fossil resource we have in an open or just thermal fuel cycle, you can see that the potential reserve of the uranium is almost nothing compared to the energy that we know today on coal, oil and gas. However, if we move to the fast neutron fuel cycle, then the same amount of uranium can produce much more energy, and then this uranium resource become the main reserve for producing electricity. So it's a total change on the paradigm if you move from the thermal to the fast fuel cycle. But to do this, we need the relevant processes, the relevant fuel fabrication, fuel reprocessing, and waste management. And the next step, it was also discussed in some workshops, is the long-term waste management with the problem of the radiotoxicity and so on. If we really look at this radiotoxicity, we know that once the plutonium is removed, the next contributor is the minor actinides and mainly the americium. And therefore, if we want to improve again the fuel cycle with a fast reactor, this is by managing the americium, by the transmutation of the americium. And therefore, we will save the waste repository resource in a deep geological repository strategy. But what has to be understood is that if we work on the life cycle assessment of all these different fuel cycles, and if we want to know more, I mentioned 2 papers addressing the current fuel cycles and future fuel cycles. In fact, and if we normalize to 1 the open fuel cycle, you can see on these pictures that if we close the fuel cycle on the French way, we already reduce the impact of the nuclear energy by 20%. In fact, mainly what we gain from the mine. If we go to the EPR, very efficient transformation of heat into electricity, then we save again some impact. We reduce the impact. When moving to the fast reactor, we change the picture. In fact, with a fast reactor, and if you have already depleted uranium, you don't need any mine. You don't need mines anymore. And most of the impact of the nuclear energy today is the mining. Okay? So a total change in the impact. So this is very important. But you can see that if you transmute the americium, in terms of environmental impact, there is almost no advantage. So transmuting the americium is not something that will save any resource, that will reduce the environmental impact of the nuclear energy. Is just to address the societal acceptance of the nuclear waste management. It could be another debate. And this is it's clear when you look at the amount of waste produced by the different fuel cycles. At the end, in terms of waste, these fuel cycles are not very different. The amount of waste is almost the same each time, even higher with the fast reactors compared to the thermal reactors. What is different is the typology of this waste that will require a lower space, a lower volume in the deep geological repository, not because of the radiotoxicity. The clay doesn't care of the radiotoxicity, just because of the heat load. And then, if we want to implement these different options, then we need the fuel cycle. We need to address the fuel fabrication and the fuel reprocessing with the dissolution and the refabrication. And if we look at the different systems that we can address, and if we look at the fast reactors plus the ADS, some of them use MOX fuel, others can use carbide or nitride fuels. I did not mention metallic fuels that are studied in the US, but poorly addressed in Europe. And the molten salt reactor that's different and are not in the frame of the projects I will mention. So, what are the common pictures of the projects I will present you? But it's the fuel cycle. That is, we need dissolution, separation, conversion, fabrication, whatever the fuel cycle, whatever the fast reactor or the ADS. And this is addressed, or this has been addressed by Success and Asgard some years ago, and now the follow-up of Success being GENIORS. A lot of separation processes have been developed for the last 25 years in the world. These separation processes could be applied to the different fuels, whatever carbide, nitride, or oxide, if we well master the head-end step, that is the dissolution. Once the fuel is dissolved, we can apply, I would say, whatever separation process. So a key issue is the dissolution. That can be a real issue for some fuels. And then also the different processes must address the different options, because we are here to provide solution to the policymakers. We are not here to decide, and therefore, by developing our processes, we provide solutions either for the, what we call the homogeneous recycling, or the actinides, including the minor actinides, in the fuel of all the assemblies, or an heterogeneous recycling where the americium, for example, is transmuted in Mira, or in blanket fuels in fast reactors. So first, Asgard, from fuel to fuel, for the non-MOX advanced fuel. This project was managed, coordinated by Chalmers University, and Christian Egberg was the coordinator, and Theodora is here if you have some question on this. You have here the budget, a huge contribution in kind from the partners is the key parameter. I will not read everything for you. The focus was, as I said, on advanced fuel, and also for the transmutation, that is CERMET and CERCER. And also training and education, but I will come back in the end. So first, the CERMET, first issue, the dissolution. So in Asgard, model systems were first studied, so cerium, molybdenum, then non-irradiated samples, plutonium oxide, molybdenum, and then irradiated samples from PETEN, where there were in these samples both plutonium and americium. And the real issue were identified on the very difficult way to dissolve these targets, in particular with the plutonium, very difficult to dissolve. We know with the classical fuels that when you have both plutonium and molybdenum, it's always very difficult. Second, CERCER. So here it's oxide of actinides in a magnesium matrix with different studies that were performed in order to study the dissolution speed, the effect of the acid, the reaction between the MgO and the media, the dissolution in the model system, and therefore the conclusion that we had in mind, but that it's easier to reprocess a CERCER than a CERMET. However, the question will be the management of the magnesia as a waste. It will be very difficult to recycle it to prepare fresh fuel, so it will be a waste. We know that it's compatible with glass, but in low amounts, so we could imagine a huge amount of waste produced with this fuel. Next step, after the separation that will be addressed in the other processes, the refabrication, the first step being the conversion, how to go from a solution to a solid with mastered properties, and different methods can be used for this based on non-powder approach. One is the salt gel methods, another one is an impregnatation of solid matrices, and the last one is the photochemical conversions. So these three options were studied in Asgard. For the fabrication, today the issues were on the nitride first. So studied on the fabrication of nitrides from salt gel or from powders. And with one issue is the measurements and the reduction of the amount of residual carbon in the fuel. Here I think Janne is somewhere maybe and is the expert in this kind of fuel. And for the dissolution of these materials, they had the opportunity to work on the real fuel from the confirmed experiments. And you have here the results of the dissolution. It's not very easy, and the hydrofluoric acid was necessary to get a total dissolution. The next category of fuel is the carbide fuel. We know by experience that carbide fuel is quite easy to dissolve. However, there is the problem of the carbon here, that at a classical dissolution produces organic species in the dissolution media, knowing that these organic species can interact with the organic solvent that we use for the solvent extraction. So the issue to fix when we want to reprocess a carbide fuel is how to remove the carbon or how to limit the impact of the residual carbon. So 2 options were studied. The direct dissolution is the first one, and there are some papers that have been published based on these results, and that's it. And there is a second option, but I have no time to describe it. It's by oxidation. It's violent, but it's very effective. So this was a very brief overview of Asgard. There is a poster for those who want more information on this project. And next is the core of the systems, is the separation processes that have been developed first for preparing, I would say, the first fuel of the fast reactors, that is from the light water reactor fuel. This is success. And in the next step is GENIORS, is the multi-reprocessing of the MOX fuel. So in success, so I would say improving the safety of spent fuel reprocessing. It is the safety not in the reactor this time, but in the reprocessing plant. And all the R&D programs were driven by safety issues. So the project had 26 partners, a total budget of 10 million for a EU grant of 50% of this total budget, and collaboration with Japan and also with the DOE. We had for the first time an INERI project between the DOE and a EU project. So this was a very useful contribution you will see in a few slides. So in success, we addressed separation processes for the 2 options, the homogeneous recycling or the heterogeneous recycling. The homogeneous concept is named GANEX, and the heterogeneous 2 options, SANEX, if you want to transmute both americium and curium, and EXAM if you only want to transmute americium. In success, what did we do? We stabilized, I would say, the different flow sheets for the 3 options. And so an ISANEX process with a hot test, a EuroExam process, the most challenging, and the EuroGANEX, knowing that the hot test, the first hot test was done at the end of the previous project, and we used the results of this hot test to improve the EuroGANEX flow sheet. I will not enter in all the detail, but if we just focus on the safety, the main issues in the reprocessing is the issues linked to the radio degradation of the media, whatever the aqueous phases or the organic phases. And therefore, we have to understand what happens when an organic phase degrades under irradiation. Because new species are created. Gaseous, so risk of increases of pressure, or still in the solution, and then potentially extracting some species, more than the reference system, or extracting species that we do not want to keep, or increasing the interaction between the aqueous and the organic phase. We call it the 3rd phase, or the red oil, if we go to the old Purex process. So and the real safety issues with this. So a lot of studies were done on the radiolytic stabilities, and these data are really important. And what we particularly did with our American colleagues is to compare different techniques for assessing the impact of the degradation. In Europe, we worked on the static tests made in CIEMAT with the NIADE facility. And in the US, at Idaho National Lab, there were some dynamic tests on the irradiation loop. And we have demonstrated that the behavior of the systems is totally different in the 2 media. And with this, finally, and it's good for processes, in a real system, the molecules are more stable than in a closed system. So this is a very important result that we get through the collaboration with the US. I will come back to these loops. It's a key tool for the studies of the safety. EuroExam, so it was the first process was developed at the CEA. It's very complex, a lot of stages. So there was a concept of a simpler process based on a new molecule named TPAEN. And through the collaboration, it was possible to implement a spike test of this process at Jülich. So 2 tests were done and demonstrated finally the low reliability on this system. That is, the data at the lab scale were very, very good, but once we went to the spike test, we highlighted a lot of drawbacks coming from the purity of the TPAEN, coming to the sensibility to some parameters, and therefore we decided to maybe forget the TPAEN and look for a new system, and then this is now in GENIORS. Just one slide to also mention that in Success there was a part of the work dedicated to pyrochemical separations. And I have highlighted this by one work that was done at ITU. Sorry, I will always call this center ITU. It will be impossible for me to change this. At ITU, and what was very nice, through the collaboration with Japan, to make a test of a process concept on irradiated fuel, the metafix fuel that was irradiated in Phoenix. So demonstrating the efficiency of a new separation system based on the use of liquid aluminum. It would be too long to explain. Also, publications are existing on this process. We had also system studies in order to know the maturity of the different processes, in order to orient the R&D program. And if you want, you can download a book from the success.eu website. Is a roadmap comparing the different processes developed in the world and proposing and explaining their level of maturity. So you can download this book, go to the website. And also global safety studies under the piloting of IRSN. They come with us for explaining us methodologies, managing workshops, brainstormings, in order to help us identifying some weak points in the different processes, again, in order to orient the next R&D programs. And then GENIORS, based on the result of Success, but this time saying, okay, we prepared the load for the first irradiation, but now we have to reprocess. It means that the new MOX we have to address is not at 8%, but maybe at 22%. The dissolution is more difficult, and the concentration of the solutions are higher. It means that we have to go deeper in the understanding of the chemical systems, in their stability, and in the different chemical risks that could arise from this. So, GENIORS is organized on the idea of a well-established scientific understanding of the mechanisms, is the green line. When we know very well the different systems, then we go back to our flow sheets and we try to improve them. And after we integrate all these results in system studies to evaluate the new process. So the project started in 2017, 24 partners, 75 million budget for a 5 million grant. And again, a new INERI project with the DOE to continue the collaboration on different issues, but mainly on the radiolytic stabilities. And the idea of GENIORS is based on what we know, is to go by down selection. We will not decide on what is the best, but we are cutting some options because we consider that they are not appropriate for the future. And then at the end, what will remain is few options on which we are really relying for the future. And just to illustrate how do we work in GENIORS and what are the first results. We looked at the EuroGAN-X. It works very well. It's very efficient. But, however, to make it efficient, we had to find some compromises that at the end are not very convenient for a large-scale implementation. We use a molecule that is named TODGA. It's very efficient to extract lanthanide and actinides. The problem is that it's not very good for managing the plutonium. There's very low loading capacity for the plutonium. And to optimize this, we had to mix another molecule in the system, DMDO-HOMA. So the system is a little complex. Here also, this increases the density of the phase. It increases the viscosity of the phase. So this is the first drawback. The second drawback is that we use a molecule in the first feed to keep some fission product in the initial solution and avoid any contamination. So this molecule is the CDTA is not so efficient also. We need a lot of it. And last, To recover selectively the transuranics, we use a molecule. Maybe you don't see it very well. These molecules that name SO3-BTP has a lot of sulfur atoms. And sulfur atoms could be an issue at the conversion when we will go from the solution to the fuel. So maybe this also is something to be fixed. Then what did we do? We went to the problem of the TODGA and we say, wait, how can we combine the effect of DMDO-HOMA and TODGA in one molecule? And by understanding the effect of the different branches on the molecule, we were able, or the University of Twente with the GRC at ITU, were able to propose a new molecule that fixed the different issues that we had. And now this molecule, MTDDGA, does not need anymore the use of DMDO-HOMA. So the system is simpler to use. And maybe for you it's not very important, but the plutonium loading limit went from below 20 grams per liter over 32 grams per liter without any third phase formation, whatever the concentration. So this is something that is really important in terms of process safety. Next, irradiation stability. What we mentioned previously is we are missing loops. And therefore, in GENIORS, we are working in comparing the different loops that exist in order to check their different properties. And then for the future, if someone wants to build a new loop, what would be the best option for having results very interesting and comparable to the rest. And this job is made together between GENIORS and the DOE. And we had already different workshops, brainstorming, and we are now organizing a round-robin test on the same system, in the same conditions, but on the different tools to check the differences. Replacing the SO3-BTP is the next step, and here also, thanks to our Italian colleague, a new molecule has been proposed, is the PTD. It's only based on CHON atoms. It means that as this molecule will remain with the actinides even at the conversion step, when we will burn the system, we do not have this sulfur atom remaining. Sulfur atom has some issues after under irradiation. There are some activation products, and so it's an issue. So here we don't have this. So this is the big also achievement of GENIORS, and with also the chance to carry out some experience by exchanging researchers between Politecnico di Milano and the CEA, and the people from Politecnico di Milano were able to work at the CEA with quantitative amount of americium and a high loading, macro concentration, that is, of course, not possible to be done at Politecnico di Milano. The ISANEX process is also under improvement, based on the results we have also for EuroGanex. The two processes are not very different, but we take the opportunity of improving GANEX to improve also ISANEX. I will not enter in the detail. And the last is the new Euro exam that for the moment is named AMCEL. And here also the idea was to find another molecules instead of the TPAEN that does not work very well. And the molecule is proposed here is an SO3-BTBP. So there is a sulfur atom, but for the moment we did not find any CHON molecules doing the job. So as we need a process, this is the option. And it will be tested as a spike test at Jülich by the end of the project. There is a backup option that is also understudied at Chalmers. How many times I still have? Okay, perfect. It's finished. This is a very innovative process. On the paper, it's much simpler, but now we have to go to the demonstration. System studies to integrate the results, process safety also to orient the R&D, fuel cycle integration to discuss with our stakeholders, and that's it. So training and education, a lot of schools have been organized, often between the different projects, student exchanges between the partners, scientific seminars, international scientific seminars, both in Success and in Asgard, And in GENIORS, we had already what we call a radical behavior workshop that we held last year in Würzburg with more than 100 attendees. So again, this is thanks to the training and education budget allocated within this EU project. Thank you very much.
Thank you very much, Dr. Bourg, for this very impressive overview, and very impressive also in, let's say, giving examples of, let's say, designing and synthesizing, let's say, new molecules that, let's say, new daughter molecules that really keeps the attractive features of parent molecules. So that seems to open a new way of a new path for research in this field. Are there any questions for Dr. Bourg? Yes, there is a question over there.
Yes, so you know my name by now. Out of the processes you study on americium extraction, which one what do you think has the greatest potential for industrialization?
Today, if we want a process for americium alone recovery, knowing the maturity of the different systems, I would use the one that was initially developed at the CEA. But just because we have not demonstrated AMCEL for the moment, it would be a mess. It's very, very difficult to master, to control, to monitor. But if we would need americium alone today, this would be the option for quite a large scale. After, if you want a small scale, solid-liquid separation, it has been done for years. We know how to separate americium from plutonium on resin columns. Well, after you have to manage the resins. It's another topic.
Other question for Dr. Bourg?
Curium. The curium is managed by the ISANEX process. So we can recover americium and curium. It's easier than recovering the americium alone. But today, everybody considers that it's of no interest because managing the curium in the fuel cycle would be a real mess. In the plant, biological protections, for the radiolytic stabilities of the system, so a lot of waste generated by the process waste, and also at the fuel fabrication. And also, you know that in all these concepts, there is an interim storage between the time you go from the waste, and the repository. And it's much easier to manage the curium by the interim storage than by transmuting it. Because do not forget that what is not in the deep geological repository is on the plants. And if you want to calculate the inventories of all the actinides that will be in the plant, if we go into the transmutation of the americium, I'm not sure that it will help in the acceptance of the nuclear energy.
Thank you, Stéphane. Now let's move to the next presentation. Do you have a question? Okay.
Just a short comment to what Stéphane just said. Actually, we can separate curium from americium. We know that usually you extract them together, they go always in parallel, but we obtain D values higher than 7. That means when you go over 1, you can already extract, even if you need several stages. But now we are up to 7, which is much, much better than we had in success when we had 3. So it is possible, but as Stéphane said, the amount of waste will be significant.
CA